Hello everyone. In this lesson, we're going to be looking at implicit differentiation. So up until now, what we've been doing is called explicit differentiation. So what this means is that we have been finding a derivative of some y function in terms of just one other variable, and this usually is x for our cases. But now what we're going to be doing is, instead of looking at the derivative of some y equals some function of x, we're actually going to be looking at the relationship between two variables and how they both actually affect the rate of change of some function. For example, let's say that we have x squared plus y squared equals 1. And this is just going to be a circle. Right, so it's a circle that is centered at 0, 0, and it has a radius of 1, meaning that it crosses at 1, 0, 0, 1, negative 1, 0, and 0, negative 1. The problem, though, is that if we wanted to try to use the derivative rules we've looked at so far, well, first of all, this would actually fail being a function, right? Because if I were to do the vertical line test and draw a vertical line through this, it passes through at 2 points, here and here. So we could actually still do this explicitly, but what we would have to do is we would have to then break this into two smaller functions, which would be, in this case, the upper half of the circle, and then also the lower half of the circle. In which case, if we were to do this, we're going to solve for y in terms of x. So first thing we're going to do, we're going to subtract x from both sides, or x squared from both sides. So we have y squared equals 1 minus x squared, and then we take the square root of both sides, which is going to give us the square root of 1 minus x squared. But we have to consider that this would be true for both the positive and the negative, so this is going to be plus or minus the square root of 1 minus x squared. So of course, that gives us this function here, f of x equals the square root of x squared minus 1. I'm sorry. This gives us the function f of x equals the square root of 1 minus x squared, and this would be the function f of x equals minus the square root of 1 minus x squared. So let's look at what this would be if we were to solve each of these explicitly. So the first one, we're going to find f prime of x, which is going to be square root of 1 minus x squared. So I'm going to rewrite this as, so first of all, rewrite this as 1 minus x squared to the 1/2 power. So if I were to take the derivative of this, then what I'm going to do is I'm going to leave this middle term alone, the 1 minus x squared. I'm going to have to the 1/2 power. So I'm going to pull that 1/2 down. So I have 1 minus x squared, and then I subtract 1 from the power. So 1/2 minus 1 is going to give me negative 1/2. And now, using our chain rule, I have to take the derivative of the inside. So the derivative of 1, which is a constant, is equal to 0. The derivative of minus x squared, I bring the 2 down. This is going to give me minus 2x. So then what I'm going to do is I'm going to put this negative 2x on top. And this, of course, over 2, because I've got the 1 over 2. The negative power makes this into the denominator. So this is going to be 1 minus x squared to the 1/2 power. And then the 2's are going to cancel. I'm going to put this back in terms of square root, just so that it's back to our original form. And I will have that this is equal to minus x divided by the square root of 1 minus x squared. For my other function, it's the same thing, except for now, instead of having 1 minus x squared to the 1/2 power, it's minus 1 minus x squared to the 1/2 power. So let me write this down real quick. This is equal to minus 1 minus x squared to the 1/2 power. So when I bring my 1/2 down, it's actually going to be minus 1/2, leave my middle alone, 1 minus x squared bring the power down by 1, so it's going to be minus 1/2. And now I'm going to multiply by, or not multiply by the derivative of the inside. Again, constant, derivative 0. Derivative of minus x squared is going to be minus 2x. So in this case, what I have minus 2x over minus 2, and then of course I have 1 minus x squared to the negative 1/2. That's going to bring it down to the bottom, so I'll just write it down again. 1 minus x squared in the denominator to the positive 1/2 power. The negative 2 will cancel with the negative 2, and I will be left with x divided by the square root of 1 minus x squared. So you can see now that we actually have two different derivatives depending on where we are on the graph. So if I'm in my upper half, what this means is that when I take the derivative, if I have a positive x value, then I'm going to end up with a negative slope. If I plug in a negative x value, what's going to happen to this? It's going to become positive, right? Minus minus, which means that I will have a positive slope. If I'm on the bottom half of my circle, when I plug in a positive x value, I'm going to get a positive slope. If I'm on the negative, one of my negative quadrants, then when I plug in negative, let's say like x equals negative 0.5, then this would make this entire thing negative. So you can see that in this case, we can actually solve for this explicitly by first breaking it into these sub-functions that are themselves actually functions. So we can solve the derivative explicitly. The problem is, though, is a circle is very easy to do that with, right? We just took the top half and the bottom half. But sometimes we're going to have much more complicated things that we want to take the derivative for, and we're going to need a way where we can find the derivative even though it is in terms of both x and y at the same time. So what do we mean when I talk about explicit versus implicit functions? So an explicit is one variable is expressed explicitly in terms of another variable. For example, we might have y equals the square root of x cubed plus 1, y equals x times sine of x, or y equals some function f of x. And notice that every one of these, it's y is equal to something in terms of just the variable x. Implicit means that we have variables are defined implicitly by a relationship between the two variables, or in this example, between x and y. So we might have something like we just did, x squared plus y squared equals something like 25, which would be a circle with a radius 5, or x cubed plus y cubed equals 6xy. In this case, we have x's and y's that can't easily be defined just in terms of one other variable. So what are the steps to solve implicit differentiation? Well, the first thing is you need to identify the implicitly defined function and the independent variable. This is usually going to be x, right? So oftentimes we'll have things in terms of x, though it doesn't have to be. It could be in terms of more than one variable. Like if you have y, it could be in terms of x and z, or if you have z, it could be x and y, something like that. Next, you want to differentiate both sides of your equation, but with respect to x. So you're going to be taking d dx of both sides. Number 3, you're then going to use the chain rule to differentiate any terms that contain y as a function of x within them. You're going to then collect all of the dy dx's to one side of your equation and everything that does not have a dy dx term to the other side of your equation. And then you're going to solve for dy dx, and this will give you the derivative of y with respect to x as an implicit function which has both x's and y's. So it's looking at as x and y change, how does the rate of change change? Let's begin by actually doing the same example we just did explicitly, but now we're going to do it implicitly. So I'm going to rewrite this a little bit differently just for my first time showing how to do this. So we're going to treat this y as the same thing as saying y as some function of x. So you could kind of think of this as this is x squared plus, and then this is some y of x, which is then squared. And you don't have to do this step. I'm just doing this so that you all can kind of see how this y isn't just y. It is y that is defined by the x that we select. So next thing we're going to do is we're going to take the derivative of both sides of our equation with respect to x. So we're going to take dy dx of the left side. So dy dx of x squared plus y of x squared plus d dx of 1. Okay, so now whenever we have a derivative of some function plus or minus some other function, we can just split that into the derivative of the first function plus or minus the derivative of the second function. So this is going to become d dx of x squared plus d dx of y of x squared, and then equals the derivative of constant is just equal to 0. So I'm just going to put 0 here. Okay, so now when we take the derivative of x squared with respect to x, this is just the normal derivative we've been doing. So this is just going to be, based on our power rule, this is going to be 2x to the first power, which is just 2x. Now when we do our yx squared, what we need to do is we first are going to treat this as, just like with the chain rule, sort of think of this as a u, right? We're not going to change it. We're just going to do the derivative of the outside. So this is going to be plus 2, leave the inside alone, so y, I'm calling yx, times, now, just like the chain rule, we have to take the derivative of what's inside that chain, in this case, u. Well, u is y of x. Well, the thing is, that's kind of the whole point of what we've been trying to do, right? We've been trying to figure out what dy dx is. We're taking the derivative of y with respect to x. So we're actually just going to write this as d dx y of x. So now if we look at what we actually have, I'm going to shorthand this now into how we actually usually write it, which is going to be 2x plus 2y y prime equals to 0. So now that we have it in terms of our y prime terms, that's this one, and our not y prime terms, which I'm going to use the set theory notation, I'm going to put a C for complement, which means not y prime. And I'm going to separate them so that I have the y prime terms on one side and the not y prime terms on the other side. So I'm going to subtract 2x from both sides, and I'm going to have 2y y prime equals minus 2x. Now the last thing I need to do is I need to get this y prime by itself though, right? I've got all the y prime terms over here, but I don't actually have y prime yet, and that's what I'm actually trying to solve for. I'm trying to solve for what is the derivative of y, which, by the way, is just dy dx. That's why I kind of changed it here. This is dy, right? So d dx of y is the same thing as saying dy dx, which we oftentimes will just write as y prime. So what I'm going to do now is I'm going to divide both sides by 2y. So this 2y is going to cancel with this 2y, and this 2 is going to cancel with this 2, and it's going to give me y prime is equal to minus x over y. So now looking at our circle, this means that my derivative is going to change by the relationship of minus xy, which you'll actually see agrees with what we had previously, because if we actually substituted back in our derivative, or our value of y, we could substitute in y that was equal to the square root of 1 minus x squared, or we could substitute in y equals negative square root of 1 minus x squared. And if we plug this in for the y we have here, you'll see that we either have this is equal to minus x over, so this one, square root of 1 minus x squared, or it could be also equal to, instead, minus over, so negative and negative gives us positive, it could be equal to x over the square root of 1 minus x squared. So see, this actually agrees with what we did. We can do this for either side now, and it's all inside of one equation versus having a separate breakout of every possible equation based on where we need to separate out our original function. So now what we're going to do is we're going to do the same idea, but we're going to change it just a little bit, and we're going to do a problem based on that. So in this example, we're going to do the same idea, except for now our circle is going to be equal to a radius of 5, right? So this means that this goes out to 5 in the right direction, it goes to negative 5 to the left, it goes up to 5 when we go above, and it goes to negative 5 when we go below, right? And these are our y values, these are x values, right? It's 5, 0, 0, 5, negative 5, 0, and 0, negative 5. So what we're going to do is first we're going to solve it implicitly like we did before, very quickly. So this is going to be d dx of x squared plus y squared equals d dx of 5. And then I'm going to split this. So this is going to be d dx of x squared plus d dx of y squared equals derivative of constant equals 0. Derivative of x squared is going to be 2x plus, derivative of y squared. Remember, you got to do chain rule. So leave the middle alone. That's your y. So you're going to bring down the 2. So you're going to get 2y to the 1 power. That's your outside of your chain. Now you're going to do the inside of your chain. What is the derivative of y? Well, again, we don't know the actual value, but what we're going to do is we're going to treat it as the derivative of y. So we have that this is equal to 0. We're going to subtract 2x. We're going to divide by 2y, and this is going to give us y prime equals negative x over y. So we have our derivative now. So now what we're going to do is we're going to find what is our tangent line when we have the point 3, 4. So when we come out 1, 2, 3, and we go up 1, 2, 3, 4. So we're going to have the tangent line to right here, which we know should be negative. So if we plug in our 3, 4, let's see what our derivative is equal to. So this is going to be equal to minus 3 over 4, or we have a slope of negative 3/4. And what we want to do now is we want to find the tangent line. So as always, we're going to plug this into our point slope formula. So we have y minus y1 equals mx minus x1, which just a reminder, when you plug in, right, this y prime is giving your instantaneous rate of change at this point, because that's what we plugged in. So that means that this is going to be, in this case, equal to our slope at the point 3, 4, which again, this slope though is based on x and y. If I were to change x, y also changes by some amount. That affects the slope of this line. So now we plug our values in. We have y minus, at this point we have a y value of 4, equals a slope of negative 3/4, x minus, and then we have an x value of 3. So solving for this, we have y minus 4 equals negative 3/4 x, and then minus a negative is going to make this plus. So if we did 3 times 3/4, you can think of the 3 as 3 over 1. So we get 3 times 3 is 9 over 4. So this is going to be 9/4. And then we're going to solve for our y. We have y equals negative 3/4 x. So we're adding 4. So this is going to be, because it's fourths, it's the same thing as adding 16/4. So 16/4 plus 9/4 is going to give me 25/4. Now we have the equation for our tangent line at the point 3, 4 on this circle that has a radius of 5. For our next example, we're going to look at what's called a folium, which we have here. The curve is described by x cubed plus y cubed minus 9xy equals 0. And if you look here, I actually have drawn out what the folium looks like, and I also will show you what it looks like in the slide. But if you look at this, there's no way that we can actually solve this in terms of just some function x, right? Because if I were to do my vertical line test, it would fail here, it would fail here, it would fail pretty much anywhere to the right of, or x equals 0, up to the point of the edge of this like little bowed out area. But the thing is, if you also look at it, it also crosses at 3 different points for all of these, right? Because this goes on forever. So I didn't really draw it that way, but this means that if we actually wanted to solve this explicitly, we would have to have something like this, where we have this part is one function, and then we have another function starting here that goes something like this. And then we have a third function which starts here and would go something like this. And this is not the only way that you could actually split this up. In fact, let me show you really quick on another slide what an example of this might be that uses a different breakdown if you wanted to solve it explicitly. So you can see on this slide, the numbers are a little bit different on this example. I have x cubed plus y cubed equals 6xy, which means that if we had it in the form that we had, it'd be minus 6xy. But either way, you can see that the way that it was split in this example is that they had the part coming down, and then they have part of the bowing up, and then the line after the little rounded part as one explicit function. And then they have this little upward part right here as a second part of a function, and then they have just this part of the line as a third part of the function. So you can see that this is 2 different ways that we could split this into 3 different functions to try to solve it explicitly. But honestly, if you tried to do that, that's going to be pretty complicated. So it's easier just to solve this implicitly. So what we're going to do for this problem is we're actually going to show that the point 2, 4 lies on this folium And then what we're going to do is we are going to find the tangent line to that particular point, right? So we're going to have some point over here, 1, 2, and then 1, 2, 3, 4, and it's going to be something here, which means I would expect that I have a positive slope to my instantaneous rate of change, or, my tangent line right there. Okay, so now what do we actually need to do? Well, just like before, we are going to take the derivative d dx of whatever we have. So this is going to be x cubed plus y cubed minus 9xy equals, d dx of 0. Just like before, I'm going to split my derivative. So this is going to be d dx x cubed plus d dx y cubed minus d dx of 9xy. But of course, I'm going to use another derivative rule, which is if I have a constant times some function, I'm taking the derivative of that, I can pull that constant out, and it's the same as the constant times the derivative of the variables inside. So this is going to be minus 9 d dx of xy equals derivative of 0. 0 is a constant, so this is just going to be equal to 0. So now let's actually evaluate our limits. So the first one we have is d dx of x cubed. So we're taking the derivative of x cubed with respect to x. So we just do our derivative like we normally do. This becomes 3x squared by our power rule. Now we're going to take the derivative with respect to x of y cubed. Now remember, we don't have x explicitly in this, but y is a function with respect to x. So what we're going to do is we're first going to use the chain rules, right? Think of your y as a u. So we're keeping it constant. So this is going to be plus 3u, which in this case is y. Use the power rule. This comes to so minus 1 gives us second power. But now we have to take the derivative of the inside of our chain, which is the derivative of y. So this is going to be 3y squared y prime. Next, we have the derivative of x times y. So this is going to actually be using our product rule, where our x is going to be our f term, our y is going to be our g term, and we're going to use gf prime plus fg prime. So doing that, this becomes, if we leave our g alone, which in this case is y, we're going to multiply that by the derivative of f. So derivative of x is just going to be equal to 1. So this is just times 1. Plus, now we're going to leave our f alone, which in this case is x, and we're going to take the derivative of our g term, which is y. But just like we talked about earlier, when I take the derivative of y, it's y of x, which means that it'll be dy dx, or y prime. I'm now going to distribute this minus 9 into this, and I'm going to have that this is equal to 3x squared plus 3y squared y prime minus 9y minus 9xy prime equals 0. So my next step is now I need to get all of my y prime terms to one side and all of my not y prime terms to the other side. So if we look at the terms we have here, this one does not have y prime, 3x squared, and minus 9y also does not have y prime. So I'm going to subtract 3x squared from both sides, and I'm going to add 9y to both sides. This is going to give me 3y squared y prime minus 9xy prime equals, I'm just going to put the positive term up front, 9y minus 3x squared. But I still haven't gotten my y prime by itself, right? I want to know what y prime is equal to. So what I'm going to do now is I'm going to, the fact that this term has y prime in it and this term also has y prime in it, I'm going to pull that y prime out, and I'm going to get y prime 3y squared minus 9x equals 9y minus 3x squared. And then I'm going to divide both sides by 3y squared minus 9x. This is going to cancel with this, and I'll be left with y prime equals, okay, I'm going to do one actual other step just to simplify things a little bit. If we look at this top, right, this right side, this top terms both have 3 in them. These bottom terms both have factors of 3 in them. So I'm going to pull a 3 out of all of these. So this top one would actually become 3, so 3 times y, minus, pull the 3 out of this, this becomes x squared, divided by pull a 3 out from each of these terms. So pull the 3 out from 3y squared, we're left with y squared, minus, pull 3 out from minus 9x will leave us minus 3x. These 3 are going to cancel, and then this means that my y prime is going to be equal to 3y minus x squared divided by y squared minus 3x. Now we have our y prime in terms of both x's and y's. So what we're going to do now is we're going to go back to the original part of the question where we wanted to find if 2, 4 is on this folium and what is the tangent line there. So first things first, we're going to plug this in to our slope to see what our slope would be if we have 2, 4. So in this case, we have x equals 2 and y equals 4. So we're going to plug those in. So this is going to be 3 times 4 minus 2 squared divided by 4 squared minus 3 times 2. So 3 times 4 is 12. 2 squared is 4, so 12 minus 4 is going to be 8. 4 squared is 16, minus 3 times 2, which is 6, gives me 10. So 8 over 10, and then if I were to simplify this, this becomes a slope of 4/5, meaning that on my folium, if I were at the point 2, 4, I have a slope of my tangent line of 4/3. So m equals 4/5, so 4 over 5. Now, last thing we want to do, as always, we want to figure out what the actual equation of our tangent line is. So what I'm going to do is I'm going to use my point slope formula. Trusty point slope formula, can't go wrong with it. We have our y value, which is 4. So this is going to be y minus 4 equals our slope of 4/5 at 2, 4, x minus, and then our x value, which is equal to 2. Solving for this, we get y minus 4 equals 4/5 x, and then minus 2 times 4 is going to give us negative 8/5. We're going to add 4 to both sides. If we think of 4 in terms of fifths, because we're adding them, this becomes 20/5. So 20/5 minus 8/5 is going to leave us with 12/5. So this should be equal to y equals 4/5x plus 12/5. And now we have the formula or equation for our tangent line, as we have a slope of 4/5 as it crosses at that point, touches at that point, 2, 4. I'm going to do things a little bit differently than I normally do. So a lot of times when I'm doing these problems, I'm actually doing them on the fly. And if I make a mistake because I'm going too fast or I'm not paying attention, I go back, I erase it, I edit it. But this one, I'm actually going to show you what the slides would show. So I didn't have these up while I was doing it. So I 100% don't know if my answer is correct until I double check at the end if I make some silly mistake. But if we look here, our solution was that we first had our x cubed plus y cubed minus 9xy equals 0. We took the derivative with respect of x on all of these terms. We then solve this. We get 3x squared plus 3y dy dx plus, minus 9 times x dy dx plus dx over dx, which is just equal to 1, times y. And then we are going to solve for this. Again, we'll get the y prime terms by themselves. We'll get the not y prime terms by themselves. We will solve for y prime, which in this case is dy dx, and we get the same thing we got. Then we plugged in our point 2, 4, and if you look here, we get that it was 8/10, which we simplified to 4/5. And then last, we plugged in our slope of 4/5, our x value of 2, and our y value of 4 into our point slope formula, and we were able to get the exact same thing. And then if you look here on this slide, you can actually see what this tangent line looks like. We've got our tangent line with a 4/5 slope touching at 2, 4, and then of course, if we wanted to, we also could ask for the normal line, which is included on this image if you were interested in that. Which we would solve by first taking our slope and taking the negative reciprocal of it. So if we have a slope of 4/5, if we wanted the normal line, our slope would then become minus 5/4. And then we would do the same thing. We would plug it into our point slope formula, but with our normal slope, which would be negative 5/4. So it'd be y minus 4 equals negative 5/4 x minus 2. solve for that, and you would get y equals minus 5/4 x plus 13 over 2. So this is something you could definitely do, but you'll notice that by solving this implicitly, instead of having 3 different derivatives and always having to worry about where we are we, if we had some set of equations where we have to say, are we in this one, are we in this one, are we in this one? Instead, we can just use our one implicit differentiation to figure out what the slope would be, regardless of what our which one we're on, right? Because it's the entire thing for our x and our y, because it actually models the relationship of x and y as you go to different parts of this folium. What about if we have higher order derivatives? So in this example, we want to find y double prime, so the second derivative of y. And we have the function, or we have the equation x to the fourth plus y to the fourth equals 16. So just like before, first thing we're going to do, just like we wanted a second derivative previously, we're going to take the first derivative, and then from there, we're going to find the second derivative. So we're going to take the first derivative, solve for y prime, and then we will take the second derivative, or take the derivative of that to get the second derivative. So first things first, we're going to take the derivative of both sides. So d dx of x to the fourth plus y to the fourth equals d dx of 16. We are then going to take d dx of x to the fourth plus d dx of y to the fourth equals d dx of a constant, right? Because there's no x in it, means that this is going to be equal to 0. d dx of x to the fourth is going to be 4x cubed plus derivative of y to the fourth is going to be 4y cubed times the derivative of y, which is going to be y prime, equals to 0. I'm going to subtract 4x cubed from both sides. This is going to give me 4y cubed times y prime equals minus 4x cubed. I'm going to divide by 4y cubed on both sides. And I'm going to have that y prime is equal to, so the 4's are going to cancel, so I'm going to have minus x cubed over y cubed. So this is my first derivative. Now, in order to get my second derivative, what I need to do is I actually need to take the derivative of this equation. So let's do that. So we have d dx of y prime equals d dx of minus x cubed over y cubed. So doing this, what do we have to do? Well, this is just going to be the quotient rule to take this derivative, right? Because this is going to be our f term, this is going to be our g term, so we have to use our quotient rule, which is going to be g f prime minus f g prime divided by g squared. So when we take the derivative of y prime with respect to x, this is actually just going to be d dx dy dx, which is then going to become dy dx squared, which is actually going to be dy y d dx. It ends up being d squared y over dx squared. But the thing is, we're just going to call it y double prime. I'll talk later on in another video about how you actually take the derivative of a derivative, and I'll show you how it actually works out to be what we're looking at. But for now, just treat it as y double prime. So now to take the derivative of this inside part, what we're going to have to do is we're going to have to leave our g alone, which in this case is y cubed. So this is going to be y cubed times, now remember, when I take the derivative, I still have to consider my y terms as a chain rule, right? So in this case, I left my y term alone. I take the derivative of minus x cubed. So the derivative of minus x cubed is going to be minus 3x squared. Minus. Now I'm going to leave my f term alone. This is going to be minus x cubed times the derivative of my g term. So just like before, I'm taking the derivative of y cubed. So in this case, it is going to be 3y squared times the derivative of the inside, which is going to be y prime. Okay, so now what I need to do is I need to simplify this a little bit. Oh yeah, I forgot prime. Now I need to divide by my g term squared. So this is going to be y cubed squared. Okay, so now let's simplify this a little bit. So first things first, I'm going to distribute this. So we're going to have y double prime is equal to minus 3x squared y cubed minus a negative is going to give me plus, so this is going to be plus 3x cubed y squared y prime over y to the 6th power to the squared, so the second power, which would be, you multiply them, this becomes y to the 6th. Now that we have substituted in our y prime as negative x cubed over y cubed, I'm going to simplify this a little bit. So first thing I'm going to do is, if I kind of think about this, this term here is the same thing as saying 3x cubed y squared times negative x cubed over y cubed. So in this case, I'm going to bring the negative forward. I'm going to bring to the x terms together, and then I'm actually going to want to get, let me write it first actually. So we'll have that this is y double prime equals minus 3x squared y cubed. Bring the negative forward. This is going to be minus 3 x cubed times x cubed, which is going to be x to the third plus 3, which is going to be x to the 6th, y squared over y cubed. And then, of course, this entire thing is divided by y to the 6th power. By the way, we do have the derivative now with respect to x's and y's, but again, we're just simplifying it because right now we have a fraction within a fraction, and we don't really like to leave it that way. So the way I'm going to fix this up is I'm actually going to multiply this first term by y cubed over y cubed. So what does this do? Well, in this case, now what this is going to be is this is going to be 3x squared. Y cubed times y cubed is going to be y to the 6th divided by y cubed. And then minus, don't forget your minus. I forgot my minus in the first one, that's why I fixed it as I said it. 3x to the 6th y squared over y cubed. And then this whole thing is over y to the 6th, which you can think of as y over 1. So now we have fractional division, right? We have a fraction divided by a fraction. So what we do is we multiply by the reciprocal, which is the same thing as saying I'm going to pull this into here, and I'll pull this one up to here, which that doesn't change it. So we now have that y double prime is equal to minus 3x squared y to the 6th minus 3x to the 6th y squared divided by y to the 9th power. And then I'm going to simplify it just a little more. First thing, both of these have a negative. I'm going to pull that out to the front. So this is going to just be minus. And then I have y to the 6th. I have y squared. So I can actually divide two of these y's. So this is going to leave me with minus 3x squared y to the 4th plus 3x to the 6th divided by y to the 7th power. And I'm pretty sure that's about as simple as we can make this. Well, I mean, I guess if you want to make it a little bit more precise, sorry, I know this is getting kind of convoluted. I could pull, this one has a 3x squared in it. This one also has a 3x squared in it. So we actually could make this minus 3x squared y to the 4th plus x to the 4th over y to the 7th. So I mean, we could simplify it that way a little bit just because it's now if we were actually plugging in x and y's, you know, we can figure out what this term is. But either way, this is how you would take the higher order derivative, is you take the derivative of your original function using implicit differentiation. You solve for y prime. Once you've solved for y prime, you then take the derivative of this and solve it for y double prime, or the second derivative. And anywhere you have y prime, you then want to plug in what you know y prime is equal to in terms of x's and y's. Plug that in, and now you have the second derivative. Of course, we did a bunch of simplification, but once we got to this step, we had the derivative. And then if you wanted to keep doing this, you want to take third derivative, you do the same thing. You take the derivative of whatever you got, right? This is y prime, double prime. You would take the derivative of this to get the third derivative, and then if you have a y prime, you plug in whatever y prime is equal to. If you have a y double prime, you plug that in. You simplify it. You can keep doing this for as many derivatives of higher order as you need to. For our last example, we want to find the first derivative. We want to find y prime if we have sine of x plus y equals y squared cosine of x. So when we're doing this, we're going to take the derivative with respect to x of both sides. So this is going to be d dx of sine of x plus y equals d dx of y squared cosine of x. So now looking at this, what are we going to have to do? Well, for the left side, we're going to have to use the chain rule, right? We're going to take the derivative of the outside, then we're going to take the derivative of the inside. For the right side, this is going to be the product rule, which technically also with the chain rule because of the y squared when we take the y prime term. So let's do our left side first. We have d dx sine of x plus y. So the first thing we do, leave the inside alone, treat this as your u, and take the derivative of sine. And that gives us cosine of x plus y. Now we take the derivative, d dx, of x plus y. All right, so let me just write that down actually. Let's not skip any steps. This would be d dx x plus y. For this one, we're going to be using the product rule where y squared is our f term, cosine of x is going to be our g term, right? And it's going to be g f prime plus f g prime. And then let's do that. So this is going to be equal to, leave g alone, which in this case is going to be cosine of x. And then we take the derivative of y squared, right? So this is going to be 2y times, remember we got to do chain rule, derivative of y, which is going to be y prime. Plus, leave f alone, y squared, and then take the derivative of cosine of x. Cosine of x gives us minus sine of x. Okay, so now let's go back to our left side. We have cosine of x plus y, derivative of x plus derivative of y, right? If we have derivative of x plus y, we can distribute this derivative to derivative of x plus the derivative of y based on our derivative rules. So if we take the derivative of x, this is going to be equal to 1 plus the derivative of y. Well, if we take the derivative of y, this is going to be equal to derivative of y, the outer part would just be 1y to the 0, which is going to be 1, and then we take the derivative of the inside, which is y, and we get y prime, right? It's still kind of a chain rule, but yeah, we're still doing y prime equals. And then I'm going to simplify this a little bit. First, on the left side, I'm going to continue to this side. I'm going to distribute the cosine, so cosine of 1, so this is just going to be cosine of x plus y, plus y prime cosine x plus y. On my left side, I have 2y prime. I'm just going to pull that to the front. This is going to be 2y prime cosine of x plus y squared times minus sine. So this is going to be minus y squared sine of x. Okay, so now you'll notice that both sides of this have y and y prime terms. Right, so we have a y prime term here, a y prime term here, a not y prime term here, a not y prime term here. So I need to get my y prime terms to one side of my equation and my not y prime terms to the other side of the equation. So this is going to, I'm going to leave this y cosine of x plus y here, and I'm going to bring this y prime term over by subtracting 2y prime cosine of x. So this side is going to be y prime cosine of x plus y minus 2y prime cosine of x equals. So now I have this term left over here, and I'm going to subtract cosine of x plus y. So this is going to be minus y squared sine of x minus cosine of x plus y. Okay, so just as before, I've got a y prime term here, I've got a y prime term here. Pull them out. So I'm going to have this side is going to be y prime cosine x plus y minus 2y cosine of x. I'm going to divide both sides by this cosine x plus y minus 2y cosine of x. So cosine x plus y minus 2y cosine of x. This is going to cancel with this, and I'm going to be left with y prime equals, I have it written differently on the slide. I have the minus cosine term up first, but it doesn't really matter. So I'm going to leave it in the way I have it. Minus y squared sine of x minus cosine x plus y divided by cosine x plus y minus 2y cosine of x. And I think the only reason I did it on the slide that way is I put the cosine of x plus y terms in the front, and then the cosine and sine with just respect to x on the left side. But either way, this is still the same thing, and we have our implicit differentiation to give us y prime. We have that y prime is equal to minus y squared sine of x minus cosine x plus y divided by cosine of x plus y minus 2y cosine of x. So you can see that it does make things a lot easier to be able to do implicit differentiation, because if we had something like this, sine of x plus y, how do we even split that, right? That becomes so much more complicated than just like we did in the beginning, where we had a circle where we could just split it easily into two explicit functions in terms of x. So hopefully this has been helpful. This is generally the topic that most Calc 1 students really seem to struggle with. And that's why I wanted to give you like a good variety of examples to kind of walk you through how we could do this based on a lot of different situations. And the key thing is just remember, anytime you're taking the derivative with respect to x on a y term, whatever that y term is, you treat the derivative like you normally would, leaving the y as a constant, right? Use substitution. But then you take the derivative of the inside, which is where you're going to get your y prime from, or dy dx. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.